These are the answers to the AP Chemistry packet that covers topics 3.2 to 3.4. On this slide, you can see Unit 3 at a glance. Unit 3 is entitled Properties of Substances and Mixtures. In this video, we will take a look at Topic 3.2, Properties of Solids, Topic 3.3, Solids, Liquids, and Gases, and Topic 3.4, Ideal Gas Law. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Topic 3.2, Properties of Solids. Here are some essential knowledge statements from the AP Chemistry course and exam description. Many properties of liquids and solids are determined by the strengths and types of intermolecular forces present. Because intermolecular interactions are overcome completely when a substance vaporizes, the vapor pressure and boiling point are directly related to the strength of those interactions. Melting points also tend to correlate with interaction strength, but because the interactions are only rearranged, in melting the relations can be more subtle. Particulate-level representations showing multiple interacting chemical species are a useful means to communicate or understand how intermolecular interactions help to establish macroscopic properties. Due to strong interactions between ions, ionic solids tend to have low vapor pressures, high melting points, and high boiling points. They tend to be brittle due to the repulsion of like charges caused when one layer slides across another layer. They conduct electricity only when the ions are mobile, as in when the ionic solid is melted, that is, in a molten state, or dissolved in water or another solvent. In covalent network solids, the atoms are covalently bonded together into a three-dimensional network, for example, diamond, or layers of two-dimensional networks, for example, graphite. These are only formed from nonmetals and metalloids. Elemental, for example, diamond, graphite, or binary compounds, for example, silicon dioxide and silicon carbide. Due to the strong covalent interactions, covalent solids have high melting points. Three-dimensional network solids are also rigid and hard because the covalent bond angles are fixed. However, graphite is soft because adjacent layers can slide past each other relatively easily. Molecular solids are composed of distinct individual units of covalently bonded molecules attracted to each other through relatively weak intermolecular forces. Molecular solids generally have a low melting point because of the relatively weak intermolecular forces present between the molecules. They do not conduct electricity because their valence electrons are tightly held within the covalent bonds and the lone pairs of each constituent molecule. Molecular solids are sometimes composed of very large molecules or polymers. Metallic solids are good conductors of electricity and heat due to the presence of free valence electrons. They also tend to be malleable and ductile due to the ease with which the metal cores can rearrange their structure. In an interstitial alloy, interstitial atoms tend to make the lattice more rigid, decreasing malleability and ductility. Alloys typically retain a sea of mobile electrons and so remain conducting. In large biomolecules or polymers, non-covalent interactions may occur between different molecules or between different regions of the same large biomolecule. The functionality and properties of such molecules depend strongly on the shape of the molecule, which is largely dictated by non-covalent interactions. Here we have a diagram on the left that represents a beaker and a close-up view of what's happening at the surface. So the first diagram shown at the right in your packet represents a sample of pure water in a beaker at room temperature. The close-up view shows a particulate model of H2O molecules near the surface of the liquid. The molecules in the liquid phase are moving at different speeds and have a range of values for kinetic energy. Some of the molecules near the surface have sufficient energy to overcome the intermolecular forces between them. They can escape the liquid phase and enter the space above the liquid surface. Eventually, the beaker will become dry when the sample of water evaporates completely. Now we have a different diagram with a flask that is sealed. So this second diagram shows a sample of pure water in a sealed flask at room temperature. The arrows in the close-up view indicate that molecules undergo both evaporation and condensation. A point is reached in this sealed container in which the rate of evaporation is equal to the rate of condensation. This is a state of dynamic equilibrium. As long as the temperature remains constant, the number of water molecules in the gas phase remains constant. Number 1. The vapor pressure of a liquid is defined as the pressure exerted by a gas in equilibrium with its liquid phase at a given temperature. The table above shows the vapor pressure of water at various temperatures. Explain why the vapor pressure of water, or any liquid for that matter, will increase when the temperature of the liquid increases. Discuss the kinetic energy of the particles in your answer. So what's going on here is that when the temperature of a sample of matter increases, the average kinetic energy of the particles of matter increase. And when liquid molecules change into a gas, they have to overcome the attractive forces between the particles of the liquid. So giving that sample of matter more energy is going to allow a greater fraction of those molecules to escape from the liquid to the gas. So when the temperature of the liquid increases, the average kinetic energy of the particles increases. At a higher temperature, a greater fraction of the particles have sufficient energy to overcome the intermolecular attractive forces and escape the liquid. This results in a greater number of gas particles in the space above the liquid surface and a higher vapor pressure. So a higher temperature, higher kinetic energy, and then higher vapor pressure. So unlike question 1, in which we were taking a sample of water and raising the temperature of the water, in question 2, we're looking at two different flasks of different liquids at the same temperature. So on the left, we see water at 20 degrees Celsius, and the vapor pressure is 17.5 torr. On the right, we see ethanol, also at 20 degrees Celsius, and the vapor pressure is 44.6 torr. So let's go ahead and answer question 2. We have parts A, B, and C. Part A, which substance, water or ethanol, appears to evaporate more easily at 20 degrees Celsius? Well, in the particle diagram, as well as the fact that the vapor pressure 44.6 is higher than that of water at that same temperature, you can see that there are more gas molecules above the liquid surface for that flask of ethanol. So the answer to part A is ethanol seems to evaporate more easily at 20 degrees Celsius. Part B, which substance, water or ethanol, is more likely to experience stronger intermolecular attractive forces in the liquid phase? And that's going to be water, because if there are fewer molecules of water vapor above the surface, then it must be more difficult for the water to change from a liquid to a gas. So more energy is required for water molecules to overcome the intermolecular forces in the liquid phase and enter the gas phase. Stronger intermolecular forces for water is going to lead to a higher boiling point. So it's going to require more energy to turn water from a liquid to a gas. Now there is this inverse relationship between the vapor pressure and the boiling point. Let's take a look at question 3. When comparing two different liquids at the same temperature, the liquid that has so for example, water on the left had a lower vapor pressure, it should have a higher boiling point. But you could have answered question 3 in the opposite direction and still been correct. Focusing on the ethanol, ethanol had a higher vapor pressure and then should have a lower boiling point. All right, let me define these two terms which are slightly different from each other. The boiling point of a liquid is defined as the temperature at which the vapor pressure of the liquid is equal to the external pressure surrounding the liquid. The normal boiling point of a liquid refers to the situation in which the vapor pressure of the liquid is equal to standard atmospheric pressure at sea level, which is usually defined as 1 atmosphere or 760 torr. In the video description area, there is a link to a video in which water is able to boil at approximately 22 degrees Celsius, and that's because a vacuum pump is used to lower the pressure above the surface of the liquid. So here we have a graph of vapor pressure on the y-axis versus temperature in Celsius on the x-axis. So when we look at this graph, we can find on the y-axis the standard atmospheric pressure, so 760 torr, and then we follow it down to, there's one curve for ethanol and there's one curve for water. So for water, if we follow that intersection of at what point does the vapor pressure of the liquid equal 760 torr, and that's when the temperature of the water is 100 degrees Celsius. So 100 degrees Celsius is the normal boiling point of the liquid. But in the video, here's a close-up view of that same curve. If they can get the pressure really, really low with that vacuum pump, then the temperature at which water will come to a boil can be approximately in the mid-20s, about 20, 25 degrees Celsius. So that would be lowering the pressure above the surface of the liquid. That is not the normal boiling point, but it is a temperature at which water will boil. Now, the question 4 is asking about ethanol. So the normal boiling point of water is 100 degrees Celsius. Use the information in the diagram to estimate the normal boiling point for ethanol. So when we follow the 760 torr to the curve for ethanol, and then look at the temperature in which that vapor pressure of ethanol is equal to 760 torr, that is approximately around 78 degrees Celsius. That's the normal boiling point of ethanol. Now I'd like to talk about the 4 different types of solids, and they are ionic solids, covalent network solids, molecular solids, and metallic solids. Particulate-level representations showing multiple interacting chemical species are a useful means to communicate or understand how intermolecular interactions help to establish macroscopic properties. So here are particulate-level representations of 4 different types of solid, starting with ionic solids. Due to strong interactions between ions, ionic solids tend to have low vapor pressures, high melting points, and high boiling points. They tend to be brittle due to the repulsion of like charges caused when one layer slides across another layer. They conduct electricity only when the ions are mobile, as when the ionic solid is melted, that is, in a molten state, or dissolved in water or another solvent. And then we have covalent network solids. In covalent network solids, the atoms are covalently bonded together into a 3-dimensional network, for example, diamond, or layers of 2-dimensional networks, for example, graphite. These are only formed from nonmetals and metalloids. Elemental, for example, diamond and graphite, or binary compounds, for example, silicon dioxide and silicon carbide. Due to the strong covalent interactions, covalent solids have high melting points. 3-dimensional network solids are also rigid and hard because the covalent bond angles are fixed. However, graphite is soft because adjacent layers can slide past each other relatively easily. So here's a close-up view of diamond and graphite. Diamond on the left, graphite on the right. So for diamond, each carbon atom is bonded to 4 other carbon atoms with tetrahedral geometry around the carbon atoms. There are covalent bonds between atoms in all directions, making diamond a hard, rigid solid with a very high melting point. In graphite, the carbon atoms form thin layers. In each layer, each carbon atom is bonded to 3 other carbon atoms in a pattern of interconnected hexagons. The layers have relatively weak intermolecular attractions between them, and the layers can slide past each other relatively easily. The next type of solid is molecular. Molecular solids are composed of distinct individual units of covalently bonded molecules attracted to each other through relatively weak intermolecular forces. Molecular solids generally have a low melting point because of the relatively weak intermolecular forces present between the molecules. They do not conduct electricity because their valence electrons are tightly held within the covalent bonds and the lone pairs of each constituent molecule. Molecular solids are sometimes composed of very large molecules or polymers. And then metallic solids. Metallic solids are good conductors of electricity and heat due to the presence of free valence electrons. They also tend to be malleable and ductile due to the ease with which the metal cores can rearrange their structure. In an interstitial alloy, interstitial atoms tend to make the lattice more rigid, decreasing malleability and ductility. Alloys retain a sea of mobile electrons and so remain conducting. There are 4 different types of solids that you should be familiar with in AP Chemistry. Descriptions of each type of solid are shown in the table below. And for each type of solid, we're going to take a look at the particles, the attractions between the particles, electrical conductivity, melting point, other properties, and then we'll look at examples of that type of solid. So let's start with ionic solids. The particles are positive and negative ions. The attractions between the particles are electrostatic attractions between oppositely charged ions. For electrical conductivity, ionic solids do not conduct electricity as a solid because the ions cannot move freely. But ionic solids do conduct electricity when they are melted or dissolved in a solvent because the ions can move freely. The melting point of ionic solids is relatively high. They tend to be hard, brittle solids, and examples of ionic solids include lithium bromide, LiBr, sodium nitrate, NaNO3, magnesium oxide, MgO, potassium chloride, KCl, copper 2 sulfate, CuSO4, and lead 2 iodide, PbI2. Now let's take a look at covalent network solids. The particles are atoms, and the attractions between the particles are covalent bonds between the atoms in a large extended network. Covalent network solids in general do not conduct electricity because the valence electrons are localized in covalent bonds. The melting point of covalent network solids is relatively high. They are hard, rigid solids, and here are 6 examples of covalent network solids. Some of them are elements, and some of them are compounds. So for the elements, examples include diamond and graphite, which are forms of carbon, and silicon. And for the compounds, examples include quartz, which is silicon dioxide, SiO2, silicon carbide, SiC, and boron nitride, Bn. Now let's take a look at molecular solids. Now for molecular, there's lots and lots of examples. So molecular solids are composed of molecules. The attractions between the particles are the intermolecular attractions, so between the molecules. Does not conduct electricity because the electrons are localized in covalent bonds. The individual particles are neutral molecules, so no ions, no free electrons. Melting point is relatively low because of the weak intermolecular forces. It's a relatively soft solid as opposed to a hard, rigid solid. And examples include iodine, so I2, carbon dioxide, CO2, methylene chloride or dichloromethane, CH2Cl2, water, H2O, naphthalene, which is C10H8, and glucose or fructose, which is C6H12O6. Lastly, metallic solids. The particles are positive metal cations, the nucleus plus the core electrons, and then the valence electrons, which we know are mobile and can move. As far as attractions between particles, it would be attractions between these positive metal cations and the sea of delocalized, mobile valence electrons. They do conduct electricity as a solid because of the mobile valence electrons. The melting points vary over a wide range, so maybe low or high, but there's no general value. And then the malleable and ductile represent properties of metals. So malleable and ductile, they can be hammered into flat sheets, and they can be stretched into long, thin wires. Examples of metallic solids: sodium, Na, magnesium, Mg, aluminum, Al, nickel, Ni, copper, Cu, zinc, Zn. All right, question 5. When a sample of solid diamond, so that's carbon, melts, covalent bonds are broken. However, when a sample of solid H2O melts, covalent bonds are not broken. Explain. So the best way to answer this question is to first identify the type of solid for each substance, and then talk about the attractions between the particles in each substance. So diamond is a covalent network solid, whereas water is a molecular solid. In a covalent network solid, the structure consists of an extended network of covalent bonds between the atoms. So when a sample of solid diamond melts, some of these covalent bonds between the carbon atoms are broken. Since water is a molecular solid, the structure consists of individual water molecules that are held together with intermolecular attractive forces. When a sample of solid H2O melts, we're not breaking covalent bonds, but rather the attractive forces in between the water molecules. So identifying the type of solid and then the attractive forces that are broken between the particles, that helps you answer this question. Question 6. We have a table with solid A, B, C, and D, and then we have descriptions of the physical appearance. We have the melting point, conductivity, and solubility. Part A. Based on this information, classify each of the 4 solids into one of the following types: metallic, ionic, covalent network, and molecular. Well, the first thing that jumps out at me in this table is solid D conducts electricity as a solid, and there's only one type of solid that can do that. So a metallic solid is the only one of the 4 types that can be a conductor of electricity as a solid because of the mobile valence electrons. So solid D should be metallic. The next thing that jumps out at me from this table is the fact that solid C is able to conduct electricity when dissolved in water. There's only one type of solid that will do that, and that's an ionic solid, which does not conduct electricity as a solid because the ions cannot move freely, but when dissolved in water, it is able to conduct electricity because now the ions can move and flow freely. So solid C is ionic. Well, now it comes down to solid A and B, which one is molecular and which one is covalent network. So the focus here would be on the difference in the melting point. So for a covalent network solid, it has a relatively high melting point because of the strong covalent bonds in all directions, whereas a molecular solid has a relatively low melting point because of the relatively weak intermolecular attractive forces in between the molecules. So the lower melting point, solid A, should be molecular, and the higher melting point, solid B, should be covalent network. Part B of this question is that now that we've identified the type of solid, we are given that they are, in no particular order, silicon, Si, nickel, Ni, naphthalene, C10H8, and potassium chloride, KCl. So make a prediction for the most likely identity of each solid. So silicon is one of those examples that I had already mentioned earlier. So there's a relatively small list of examples of covalent network solids. I would encourage you to just be familiar with these examples because that's the best way to know what we're talking about. With respect to the next solid type, it says nickel, Ni. Here is a diagram of the metals, nonmetals, and metalloid. Technically, Si, silicon, is a semi-metal or a metalloid, but in general you can see that those black and gray classifications on the right side of the periodic table, boron, silicon, germanium, arsenic, antimony, and tellurium, are metalloids, but nonmetals would include carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine, selenium, bromine, iodine, and all the noble gases. Hydrogen is also a nonmetal. So the vast majority of the elements in the periodic table are classified as metals. Potassium, titanium, manganese, iron, and of course nickel is definitely an example of a metal. Now for the next example, it says naphthalene, C10H8. If I have carbon and hydrogen, which are both classified as nonmetals, when they form compounds, generally two or more nonmetals will produce covalent molecular compounds. So that's going to make naphthalene the molecular solid. And of course, that last example, potassium chloride, is metal and nonmetal. So when you typically see a binary compound composed of two elements where one is a metal and one is a nonmetal, like this example, that should be an ionic solid. All right, we've classified in part A the four types of solids based on the properties. We've identified, based on the chemical formula, the four types of solids. And now moving on to question 7. Question 7 says, use principles of interparticle forces to explain the difference in the properties of the two substances shown in the table above. So the first substance is SiH4, and the second substance is SiO2. We can tell, looking at the numbers for melting point and boiling point, that SiO2 has a much higher melting point and boiling point than SiH4. If you don't know about how to go from Celsius to Kelvin or what room temperature represents, I'll tell you that room temperature is approximately 25 degrees Celsius or about 300 Kelvin. So the fact that SiH4 boils at 161 Kelvin, it turns out that SiH4 is actually a gas at room temperature. So you'd have to cool it down to become a liquid and eventually cool it down even more to have it freeze. SiO2 melts at a very high temperature and obviously boils at an even higher temperature. So SiO2 is a solid at room temperature with strong attractive forces, and SiH4 is a gas at room temperature with very weak attractive forces between the particles. So SiH4 is very similar to a compound called methane, CH4, also a gas at room temperature. SiH4 consists of molecules, individual particles of SiH4 with relatively weak intermolecular attractive forces between the molecules. And since it's a nonpolar molecule, it would experience only London dispersion forces. On the other hand, SiO2 is one of the examples I asked you to memorize: diamond, graphite, silicon, quartz, SiO2, and then silicon carbide and boron nitride. So since SiO2 is an example of a covalent network solid, atoms of silicon and oxygen, extended network of strong covalent bonds between the atoms. So we have to explain the difference in properties. Since SiH4 is composed of molecules and experiences relatively weak London dispersion forces in between those molecules, and SiO2 is a network covalent compound with strong covalent bonds between the atoms of silicon and oxygen, that explains why the difference in properties, that LDFs, or London dispersion forces, are much weaker than the covalent bonds. So the attractive forces between the particles in SiO2 are much stronger than the attractive forces between the particles in SiH4. So SiO2 has a much higher melting point and boiling point than SiH4, much stronger interparticle attractive forces. Question 8. The structures and melting points for methyl salicylate on the left and salicylic acid on the right are shown above. The same three types of intermolecular forces, London dispersion forces, dipole-dipole interactions, and hydrogen bonding forces exist among molecules of each substance. Explain why the melting point of salicylic acid, which is 159 Celsius, is much higher than that of methyl salicylate, which is -9 degrees Celsius. So the first thing that I'm going to do is compare the relative size of the electron cloud for each molecule. I'm going to start by counting carbon atoms. So for methyl salicylate, that would be 1, 2, 3, 4, 5, 6, 7, 8 carbon atoms. And then I see 8 hydrogen atoms and 3 oxygen atoms. So C8H8O3. For the salicylic acid molecule on the right, I'll start counting the carbon atoms. 1, 2, 3, 4, 5, 6, 7 carbon atoms. I see 6 hydrogen atoms and 3 oxygen atoms. So C7H6O3. So they're very similar, but I would say methyl salicylate has a slightly larger electron cloud. Well, the size of the electron cloud, or the relative strength of the London dispersion forces, is not going to help us here. It's not going to explain why the salicylic acid molecule, which is on the right, actually has a much higher melting point than the methyl salicylate on the left. So size of the electron cloud is not going to help me here. I don't think dipole-dipole interactions are going to be very different. These are both polar molecules, but something special is going to happen with respect to hydrogen bonding interactions between molecules. So let's take a look. How do I explain why salicylic acid on the right has a higher melting point than methyl salicylate on the left? Now, there are 8 hydrogen atoms in methyl salicylate, but only one of them is directly bonded to oxygen. So that hydrogen atom that I'm highlighting in that molecule on the left, it can participate in hydrogen bonding attractions with neighboring molecules. If I look at the salicylic acid, I see actually 2 different hydrogens that are directly bonded to oxygen. So there are 2 different locations in the same molecule in which a hydrogen bonding interaction between molecules can occur. So I have 1 hydrogen bonding site in methyl salicylate, and I have 2 hydrogen bonding sites in salicylic acid. So that's the important distinctive feature that's going on here. Molecules of salicylic acid have more hydrogen bonding sites than molecules of methyl salicylate. So therefore, this leads to stronger intermolecular forces, attractive forces between the molecules, and a higher melting point for salicylic acid. Okay, now it's time to move from topic 3.2 to topic 3.3. Topic 3.3, solids, liquids, and gases. Here are the essential knowledge statements from the AP Chemistry course and exam description. Solids can be crystalline, where the particles are arranged in a regular 3-dimensional structure, or they can be amorphous, where the particles do not have a regular orderly arrangement. In both cases, the motion of the individual particles is limited, and the particles do not undergo overall translation with respect to each other. The structure of the solid is influenced by interparticle interactions and the ability of the particles to pack together. So that has to do with solid particles being relatively close to each other and not moving around very much. The constituent particles in liquids are in close contact with each other, and they are continually moving and colliding. The arrangement and movement of particles are influenced by the nature and strength of the forces, for example, polarity, hydrogen bonding, and temperature between the particles. The solid and liquid phases for a particular substance typically have similar molar volume because in both phases, the constituent particles are in close contact at all times. So again, the message so far is that the particles of solid and liquid are fairly close together, although liquid particles can move a little bit more than solids. And then finally, in the gas phase, the particles are in constant motion. Their frequencies of collision and the average spacing between them are dependent on temperature, pressure, and volume. Because of this constant motion and minimal effects of forces between particles, a gas has neither a definite volume nor a definite shape. So here's a particulate diagram of a solid, a liquid, and a gas for 6 molecules of nitrogen. So solids and liquids pretty close together, gases farther apart. So looking at topic 3.3, that's pretty much all I wanted to mention in this video, so I don't have any example problems for this. I'm going to move on from topic 3.3, so relatively brief and straightforward, to topic 3.4. Topic 3.4, Ideal Gas Law. Here are some essential knowledge statements from the AP Chemistry course and exam description. The macroscopic properties of ideal gases are related through the ideal gas law, and the equation is P times V equals N times R times T, where P is pressure, V is volume, N is number of moles, T is the absolute temperature, and R is the ideal gas constant. In a sample containing a mixture of ideal gases, the pressure exerted by each component, which is the partial pressure, is independent of the other components. Therefore, the partial pressure of a gas within the mixture is proportional to its mole fraction, and the total pressure of the sample is the sum of the partial pressures. So here are two equations that relate to gas mixtures. The first equation is saying that the partial pressure of gas A is equal to the total pressure of the gas mixture times the mole fraction of component A, where the mole fraction is a ratio of moles of A divided by the total moles of gas in the mixture. And the other equation is saying that the total pressure of the gas mixture is equal to the sum of the individual partial pressures of the various gases in that mixture. So those components could be A, B, and C. So the partial pressure of A plus the partial pressure of B plus the partial pressure of C, etc. Graphical representations of the relationships between pressure, volume, temperature, and number of moles are useful to describe gas behavior. In the video description area, there is a link to the PhET simulation on gas properties, and I'll be using video clips from that PhET simulation as I describe the properties of an ideal gas. Gas particles are in constant random rapid motion. Gases expand to fill their container completely. And as you can see in this video clip, where they remove the divider between two gas samples, two or more gases will form a homogeneous mixture when they are combined together, and that is due to the random motion of the gas particles as they collide with each other. Gases are highly compressible, and you can see in this video clip that the volume of the gas sample can be reduced dramatically, and that's because there's lots of empty space in between the gas particles. The volume of the gas particles themselves is negligible compared to the volume occupied by the gas. So that word negligible means that the volume of the gas particles is so much smaller than the volume occupied by the gas that we can ignore as insignificant the volume of the gas particles themselves. It's much smaller than the volume occupied by the gas sample. Collisions of gas particles are perfectly elastic, meaning that energy is transferred but not lost during collisions. And for an ideal gas, there are no attractive or repulsive forces between the gas particles. Here is a portion of the AP Chemistry equations and constant sheet that includes information about gases. So I'd like to highlight selected equations on this equation sheet. The first equation is known as the combined gas law equation, and it relates the variables P, V, and T, which are pressure, volume, and the absolute temperature. So the equation is P1 times V1 divided by T1 is equal to P2 times V2 divided by T2, where the 1 and the 2 would represent the initial and the final conditions for a gas sample. So it shows you how pressure, volume, and temperature are related to each other. The next equation, which is the ideal gas law, involves pressure times volume is equal to number of moles times the ideal gas constant R times the absolute temperature. The next two equations relate to a mixture of gases. So this equation is defining the partial pressure of one gas in a gas mixture as the pressure of component A. So the pressure of component A is equal to the total pressure of the gas mixture times the mole fraction of component A. And the mole fraction is a ratio, moles of A divided by the total moles of gas in the gas mixture. And the total pressure of the gas mixture is equal to the sum of the individual partial pressures of each component in that gas mixture. So I had mentioned the ideal gas law, and R is the ideal gas constant, and the units that are associated with the ideal gas constant, which has a value of 0.08206, those units are liters for gas volume, atmospheres for gas pressure, Kelvin for the absolute temperature of the gas, and mole for the number of moles of gas. Also, on the equation sheet, you can see a conversion between Kelvin and Celsius. So what we typically do is we add 273 to the Celsius temperature to convert the temperature from Celsius to Kelvin. You can also see a conversion between units of pressure. 1 atmosphere is equal to 760 millimeters of mercury, or 760 torr. Now, let's take a look at the relationships between gas variables. And those gas variables are pressure, volume, number of moles, and the absolute temperature. So in this table, you can see that I'm taking a look at relationships between two gas variables and then holding the other two variables constant. So in our first comparison, it says that pressure is inversely proportional to volume when the number of moles and the absolute temperature is held constant. And then for the other four relationships in the table, those are direct proportions. So for example, pressure is directly proportional to the absolute temperature, pressure is directly proportional to the number of moles, volume is directly proportional to the number of moles, and then finally, volume is directly proportional to the absolute temperature. So in each of the relationships, two variables are changing, and the other two variables are held constant. You can see in the far right column of this table that each of these relationships between gas variables can be described by a mathematical equation. So let's go ahead and use the PhET simulation for gas properties to explore each of these 5 relationships between gas variables. So our first one is that pressure is inversely proportional to volume. Now you can see that represented by the diagram, by the graph. And in the PhET simulation, what's happening is that the volume of the gas sample is decreased to half its original value. and as a result, the pressure of the gas sample is doubled. So the volume decreases by half, the pressure is doubled, and the variables that are not changing are the number of moles, or the number of gas particles, and the absolute temperature. Now, in our next relationship, it's going to be that pressure is directly proportional to the absolute temperature of the gas. So in this FET simulation, the gas sample is being heated from an initial temperature of 300 Kelvin to a final temperature of 600 Kelvin. So as a result of doubling the absolute temperature of the gas, the pressure of the gas sample is also doubled. So you can see that as a direct relationship in the diagram, in the graph, and the variables that are not changing, the ones that are held constant, are the number of moles, or the number of gas particles, and the volume of the gas sample. So as we double the absolute temperature of the gas, the pressure of the gas sample is also doubled. Now, in our next relationship, it's going to be between pressure and the number of moles. So you can see a direct relationship here. And in the FET simulation, what I'm doing is I am doubling the number of particles of the gas sample. And when that happens, the pressure of the gas sample is also doubled. The variables that are not changing, the ones that are held constant, are the absolute temperature of the gas and the volume of the gas sample. So double the number of moles, double the pressure of the gas sample. Our next relationship involves volume and number of moles. So here we have another direct relationship. So what I'm doing in the FET simulation is I'm doubling the number of particles of the gas sample, and as a result, the volume of the gas sample is also doubled. The variables that are not changing are the absolute temperature and the pressure. So temperature and pressure remain constant, but when I double the number of moles, or the number of particles of gas, the volume is also doubled. And our last relationship here is between volume and temperature. Again, another direct relationship. So what I'm doing in the FET simulation is I'm heating the gas sample from an initial temperature of 300 Kelvin to a final temperature of 600 Kelvin. And as a result, the volume of the gas sample is also doubled. So the variables that are not changing are the number of moles, or the number of gas particles, and the pressure. So when the temperature, the absolute temperature of the gas sample is doubled, the volume of the gas sample is also doubled. All right, now we are ready to take a look at question 9 in your packet. Question 9 says, a student was assigned the task of determining the molar mass of an unknown gas. The student measured the mass of a sealed 843 milliliter rigid flask that contained dry air. The student then flushed the flask with the unknown gas, resealed it, and measured the mass again. Both the air and the unknown gas were at a temperature of 23 degrees Celsius and a pressure of 750 torr. The data for the experiment are shown in the table below. Part A. Calculate the mass in grams of the dry air that was in the sealed flask. So according to the data in the data table, the volume of the sealed flask is 843 milliliters, and we are given that the density of dry air at this temperature of 23 degrees Celsius and a pressure of 750 torr, that density is 1.18 grams per liter. So to calculate the mass of the dry air that was in the sealed flask, we're going to use density as a conversion factor to convert from volume into mass. So let's start with the volume of the sealed flask, which is 843 milliliters. Since density is in grams per liter, first, let's convert the units of milliliters into liters. And you should know that there are 1,000 milliliters for every 1 liter. So that's my first conversion factor. Now I'm going to put 1.18 grams on top and 1 liter on the bottom so I can get my units of liters to cancel out. And again, I'm converting from volume into mass using density as a conversion factor. So when I pick up my calculator, it's going to be 843 divided by 1,000 times 1.18. And when I do that math, I get an answer of 0.99474 grams. Now I'll round off my answer to 3 significant figures based on the measurements that I was given. So that will work out to be 0.995. So that is my answer to part A of this question. Now let's take a look at part B of this question, which says, calculate the mass in grams of the sealed flask itself. That is, if it had no air in it. So our answer to part A, which is the mass of the sample of dry air, is 0.995 grams. And according to the information in the data table, the mass of the sealed flask and the dry air has a combined value of 157.70 grams. So all we have to do is subtract these two values. So 157.70, the combined mass of the flask and the dry air, minus 0.995 grams, the mass of just the air, that will give us a value of 156.705 grams. And what I'm going to do is round off this answer so that it matches the precision of the scale that was used in this experiment, which means I'm going to round it off to 2 decimal places. So my answer to part B is 156.71 grams, the mass of the empty sealed flask. Now let's take a look at part C of this question, which is talking about the unknown gas. So part C says calculate the mass in grams of the unknown gas that was added to the sealed flask. So remember that in part B, we have just determined that the mass of the sealed flask itself, with nothing in it, has a value of 156.71 grams. And looking at the data in the table, the combined mass of the sealed flask and the unknown gas is 158.08 grams. So all we have to do now is just subtract those two values. So 158.08, the combined mass of the flask and the unknown gas, minus the mass of just the flask itself, 156.71. That difference gives us the answer to part C. So 1.37 grams represents the mass of the unknown gas that was added to the sealed flask. Now, at the beginning of question 9, it said, a student was assigned the task of determining the molar mass of an unknown gas. So we're about to do that calculation in part D to determine the molar mass of the unknown gas. So in part D, it says, using the information above, calculate the value of the molar mass of the unknown gas. So the units of molar mass are grams per mole. In other words, grams divided by moles. In part C, we have already determined that the mass of the unknown gas is 1.37 grams. So what we need to do is figure out the number of moles of gas. And this will involve using the ideal gas law equation. So how are we going to determine the number of moles of the unknown gas? Well, considering that the ideal gas law involves pressure, volume, number of moles, and absolute temperature, if we already know the pressure, the volume, and the temperature of this gas sample, then we can calculate the number of moles of gas in the sample. And for R, which is the ideal gas constant, we're going to use a value of 0.08206, and the units of volume should be in liters, the units of gas pressure should be in atmospheres, and the units of temperature should be in kelvins. So PV equals nRT is the ideal gas law, and we're solving for the number of moles of this gas. That would be N. So N is equal to P times V divided by R times T. So that is our setup to calculate the number of moles of gas, which we can use to determine the molar mass of the unknown gas. Now, for gas pressure, we were given a value of 750 torr, but we have to convert that into units of atmospheres. So if you look on your AP Chemistry equation sheet, you can see that there is a unit conversion that says 1 atmosphere is equal to 760 torr. So that's going to be our conversion factor. 750 torr times 1 atmosphere over 760 torr to convert the units from torr to atmospheres. So I'll pick up my calculator and do 750 divided by 760, and I get a value of 0.987 atmospheres. So that's the pressure I'm going to use in this calculation. Now for the volume, it has to be in units of liters, which means I will take 843 milliliters, which is the volume of the gas, and simply convert that into liters. That involves dividing by 1,000. When you go from milliliters to liters, you divide by 1,000. So that value becomes 0.843 liters. Remember that on the equation sheet, it tells you that the ideal gas constant, R, is 0.08206. So I'm going to go ahead and write that value. According to the units, it's going to be liters, atmospheres per mole per Kelvin. And the temperature right now is given to us in units of Celsius. So I take 23 degrees Celsius, and then I add 273 to that value. So 23 plus 273 gives me a value of 296 Kelvin. So now my setup for calculating the number of moles of gas is complete. So when I pick up my calculator, it will be 0.987 times 0.843 divided by 0.08206 divided by 296. So when I do that math, I get 0.03425 mole. I'm not going to round off that answer because that's not my final answer, but that is the number of moles of gas, the unknown gas. Since the units of molar mass are grams per mole, that means I will take the grams, which is 1.37, and I will divide by the number of moles that I just calculated using the ideal gas law. So 1.37 divided by 0.03425 will give me an answer for grams per mole. And when I do that math, I get a value of 40.0. So the molar mass of the unknown gas is 40.0 grams per mole. That's the answer to part D of this question. Now let's take a look at the next part of this question. This is part E. It says, after the experiment was completed, the instructor informed the student that the unknown gas was carbon dioxide. Carbon dioxide has a molar mass of 44.0 grams per mole. Calculate the percent error in the value of the molar mass calculated in part D. So to do this calculation, we have to know the formula for calculating percent error. So here is the formula for calculating percent error. You take the difference between the two values, which are the experimental value that was determined based on the laboratory data. You subtract the accepted value or the known value, and that difference will be represented as an absolute value. You divide that difference by the accepted value and then multiply by 100. So remember that in part D, the experimental value that we had determined for the calculated value for molar mass of the unknown gas, that was 40.0. But the accepted value for the molar mass of carbon dioxide is 44.0. So the difference between 40 and 44 would be 4. It's not negative 4 because we're going to take the absolute value. So 4 divided by 44 and then times 100. So if we do that math, 4 divided by 44 times 100, we get 9.1% error. So that is the value for the percent error for this particular experiment. Now let's move on to part F of this question. In part F, we are given two different occurrences, occurrence 1 and occurrence 2. For each of the following two possible occurrences, indicate whether it, by itself, could have been responsible for the error in the student's experimental result. So what exactly is the error? Well, the error is that the calculated value for the molar mass of this gas is less than the accepted value. So we're going to consider each of these two occurrences separately and determine whether or not that would cause the calculated value for the molar mass of the gas to be too low. You need not include any calculations with your answer, but for each of the possible occurrences, justify your answer. So let's start with occurrence number 1. In occurrence number 1, it says the flask was incompletely flushed with carbon dioxide, resulting in some dry air remaining in the flask. In other words, they had a flask filled with dry air. They flushed out the dry air, replacing it with CO2. But what if that flushing procedure was incomplete? Then there would still be a little bit of dry air mixed in with the carbon dioxide. Now, if we look at the data in the table, we already know that the mass of the sealed flask and dry air is 157.70, and when that was replaced with the unknown gas, or carbon dioxide, it was 158.08. That's heavier. So that means that dry air weighs less than CO2, or you could say that dry air has a lower density than CO2. So if dry air weighs less or has a smaller density than CO2, suppose that occurrence 1 resulted in a mixture of dry air and CO2. Well, that combined mixture would weigh less than pure CO2. So if the gas in the flask were a mixture of CO2 and dry air, the total mass of the gas would be less than if it were pure CO2. Well, if your mass is too small, then your calculated value for molar mass would be too small. So the answer is yes, occurrence number 1 could have been responsible for the error in the student's results in this experiment, because a little bit of dry air would cause the mass to be too low, and therefore the calculated value for molar mass to be too low. Now let's move on to occurrence number 2. So a different situation. Now it says the temperature of the air was 23 degrees Celsius, but what if the temperature of the carbon dioxide gas was lower than the reported 23 degrees Celsius? In other words, it was too cold. Its temperature was less than 23. Let's consider what would happen if a gas sample is at a lower temperature. What happens in terms of colder gas, and how would that affect the density? You may already know from a popular phrase which is that warm air rises and cold air sinks, that whenever you increase the temperature of a gas, the density goes down, and when you decrease the temperature of the gas, the density goes up. But let's go ahead and consider mathematically why that occurs. Why does warm air rise and cold air sink? Well, here on this graph, we can see a direct relationship between temperature and volume. So if you decrease the temperature of a gas, its volume will decrease under conditions of constant number of moles and pressure. So a colder sample of gas should occupy a smaller volume, and since density equals mass divided by volume, we can say that a colder sample of gas should have a larger density. So the same mass of gas would be present in a smaller volume. So if they flushed the flask with a gas that was even more dense because of its lower temperature, that would result in the mass being too high. So a greater density because of this colder gas would only cause the mass to increase. That's not what happened in this experiment. So if that carbon dioxide had been too cold, it would have increased the density and therefore increased the mass. So occurrence number 2 could not have been responsible for the error in the student's results in this experiment. All right, now let's move on to part G of this question, which talks about how you would determine the volume of the rigid flask. So part G says, describe the steps of a laboratory method that the student could use to verify that the volume of the rigid flask is 843 milliliters at this particular temperature. You need not include any calculations in your answer. Well, one of the easiest methods to determine the volume of the rigid flask would be to take that flask and fill it to the brim with liquid. Since gases expand to fill their containers completely, we could fill that flask all the way up to the top and then carefully transfer that into a graduated cylinder. Record the volume and verify if the volume is 843 milliliters. Another method involves connecting mass to volume using density. So instead of actually transferring the liquid into a graduated cylinder, you could first record the mass of the empty flask with nothing in it, and then fill the flask to the brim with a liquid of known density, so such as water, for example. Now that you have the mass of the liquid-filled flask, subtract to find the mass of the liquid. And if you know the mass of the liquid that filled that flask, you could use mass and density to calculate volume. So you could take the mass, divide by the density to calculate the volume. All right, well, that's the end of this particular question. That was part G. Now, let's take a look at question 10 in your packet. Question 10 says a pure sample of a gas has a density of 1.31 grams per liter at a pressure of 1 atmosphere and a temperature of 25 degrees Celsius. What is the molar mass of this gas? Propose a possible identity of this gas. So back in question 9, we needed to do a calculation to determine the molar mass of an unknown gas. And in that calculation, in question 9, we used the ideal gas law. So what we did in that calculation was we plugged in the values that we knew for pressure, volume, and temperature, and we calculated the number of moles of gas. So we can do a similar calculation here in question 10. Remember that the R, which is the ideal gas constant, is 0.08206, and the units of volume should be in liters, the units of pressure should be in atmospheres, and the units of temperature should be in Kelvin. So do we already know the pressure and the temperature? Yes, those values are given. So here is the ideal gas law, PV equals nRT. We're going to go ahead and try to calculate the number of moles of gas, but we have to make an assumption about the volume of the gas. That wasn't given to us in this question. So let's go ahead and assume that we have exactly 1 liter of gas. So the density of the gas is 1.31 grams per liter. Let's assume that we have exactly 1 liter of this gas. So now, based on that assumption, we know the volume is 1 liter. We are given that the pressure is 1 atmosphere. And although the temperature is 25 degrees Celsius, we know how to convert from Celsius to Kelvin. So if you add 273 to the Celsius temperature, you get the Kelvin temperature. So 25 plus 273 is 298 Kelvin. So now we know the volume, the pressure, and the temperature, and we can calculate the number of moles. Let's go ahead and set up that calculation. So N equals P times V divided by R times T. Pressure is 1 atmosphere. We're assuming that the volume is 1 liter. The ideal gas constant is 0.08206, and our Kelvin temperature is 298. And if we do this math, 1 times 1 divided by 0.08206 divided by 298, we get a value of 0.0408933. And I'm not rounding off this answer just yet because I'm not done with my calculation. So we're looking for molar mass. Now the units of molar mass are grams per mole. In other words, grams divided by moles. If we go back and remember that that's 1.31 grams per liter, we made the assumption that it was a 1 liter sample of gas. Now we know that the mass of this sample of gas is 1.31 grams. We just calculated the number of moles from the ideal gas law. So grams divided by moles will give us the molar mass. So 1.31 divided by this particular value for the number of moles, we get our answer that the molar mass of this gas is 32 grams per mole. And a common gas that you're probably familiar with in terms of the calculated value for molar mass would be diatomic oxygen, or O2. So the molar mass of O2 is 32 grams per mole. So a possible identity of this gas is oxygen gas, or O2. So that is the answer to question 10. Now let's take a look at question 11. In question 11, it says, a gas mixture contains 14 grams of nitrogen gas, N2, and 32 grams of oxygen gas, O2. The total pressure of the gas mixture is equal to 1200 torr. Calculate the partial pressure of each gas in the mixture. Now, since partial pressure is related to mole fraction, it would be important that we start off this problem by calculating the number of moles of each gas. So we are given grams of each gas, but we need to calculate the number of moles of each gas. And so from the information on the periodic table, we can see that the molar mass of nitrogen, N2, works out to be 28 grams per mole. And using the periodic table, we can realize that the molar mass of oxygen gas, O2, is 32 grams per mole. Now, this gas mixture contains 14 grams of nitrogen gas. Since 14 is exactly half of 28, that means that we have a half a mole of nitrogen gas. And we are told that we have 32 grams of oxygen gas, so that would be 1 mole of oxygen gas. So now we have successfully calculated the number of moles of each gas. Since mole fraction is a ratio of moles of each gas divided by the total number of moles in the gas mixture, the total number of moles for this particular gas mixture would be 1.5. We're just adding those two number of moles together. Now, let me just remind you on the equation sheet that the partial pressure of one gas in a gas mixture is equal to the total pressure of the gas mixture times the mole fraction. And the mole fraction is a ratio of moles. Moles of one particular gas divided by the total number of moles of the gas mixture. So in this problem, it would be 0.5 divided by 1.5. The mole fraction of nitrogen would be 1/3, or 0.333. And the mole fraction of oxygen gas would be 1 divided by 1.5, and that works out to be 2/3, or 0.667. So 1/3 of this gas mixture is nitrogen, 2/3 of this gas mixture is oxygen, again using mole fraction. The total pressure of the gas mixture is 1200 torr. So 1/3 of 1200 is 400 torr. That's the partial pressure of nitrogen in this mixture. And 2/3 of 1200 is 800. So these values, 400 torr and 800 torr, correspond to the partial pressure of nitrogen gas and the partial pressure of oxygen gas, respectively. And it makes sense that the partial pressure of oxygen is twice as much as the partial pressure of nitrogen, since moles and pressure are directly proportional. If we have twice as many moles of oxygen gas, then the pressure of oxygen gas should be twice as much relative to nitrogen. So these are the correct answers to question 11. Now, let's take a look at question 12. In question 12, it says, in the diagram above, two flasks are connected by a valve that is closed. The flask on the left contains 10 liters of hydrogen gas at a pressure of 3 atmospheres. The flask on the right contains 4 liters of methane gas, or CH4, at a pressure of 2 atmospheres. Part A. Calculate the total pressure of the system after the valve is opened and the two gases are mixed completely. Assume that the temperature remains constant and that the total volume of the gas mixture is equal to 14 liters. In other words, 10 plus 4 would be 14 liters. Now, in this problem, we are given two different pressures. We're given a pressure of 3 atmospheres for the hydrogen and a pressure of 2 atmospheres for the methane. And it's very tempting to simply take those two pressures and add them together. 3 plus 2 is 5. But we can't do that. The pressure of the hydrogen right now is 3 atmospheres. The pressure of the methane right now is 2 atmospheres, but the valve is closed. And so we can't just simply add these two pressure values together, because each gas right now occupies a separate container. And once that valve is opened, each gas will expand into a larger total volume of 14 liters. And when volume increases of a gas sample, assuming constant temperature and number of moles, the pressure will decrease. So you can see on this slide something I had mentioned earlier in this video, that there's this inverse relationship between pressure and volume. So you can see from the PhET simulation that when we decrease the volume, the pressure is going to go up. And when we increase the volume, the pressure is going to go down. So in fact, we cannot simply add 3 plus 2 is 5, because once the valve is opened, the partial pressure of the hydrogen will be less than 3 atmospheres, and we don't know what that value is at the moment. And once the valve is open, the partial pressure of the methane will be less than 2 atmospheres, and we don't know what that value is. So it's not going to just be 3 plus 2 is 5. What we're going to need to do is to use that equation that is highlighted in the top right corner of this slide, and that is P1 times V1 equals P2 times V2. That mathematical relationship between pressure and volume represents the inverse relationship between pressure and volume. Okay, so for hydrogen, P1, the initial pressure of the hydrogen is 3 atmospheres. V1, the initial volume of the hydrogen before the valve is opened, is 10 liters. But after the valve is opened, the new pressure will be some number that we don't know yet. It's going to be less than 3 atmospheres. And once the valve is opened, the new volume occupied by the hydrogen is 14 liters. So P1 times V1 equals P2 times V2. Let's plug in the numbers that we know and solve for the final pressure of the hydrogen once the valve is opened. And so the math for this calculation would be 3 times 10 divided by 14. So that works out to be a value of 2.14. So the pressure of the hydrogen after the valve is opened is 2.14 atmospheres. Now let's repeat that calculation for the gas on the other side of the diagram, the methane. So for the methane, CH4, the initial pressure before the valve is opened is 2 atmospheres. The initial volume occupied by the gas before the valve is opened is 4 liters. Now, once the valve is opened, the new pressure of the methane will be some number that we don't know yet. It's going to be less than 2 atmospheres. And once the valve is opened, the volume occupied by the methane will be 14 liters. So P1 times V1 equals P2 times V2. Let's plug in the values that we know so we can solve for the pressure of the methane after the valve is open. So the math involved here will be 2 times 4 divided by 14. So when we do that math, we get 0.571 atmospheres. That is the pressure of the methane after the valve is opened. So now we have calculated the final pressure of the hydrogen after that valve is opened, and we've calculated the final pressure of the methane after the valve is opened. So now we can just simply add those two values together because the total pressure of a gas mixture is the sum of the partial pressures. So once we've determined the final pressure of hydrogen and methane, we can simply add these two values together. So the correct answer to part A, the total pressure of the system after the valve is opened, is 2.14 plus 0.571, and that gives us a value of 2.71 atmospheres. I just rounded off my answer to 2 decimal places for this answer. So when you're adding two different values together, the rules for rounding would be that you go with the least number of decimal places. So 2.71 atmospheres, that's the answer to part A. Now let's move on to part B of this question. In part B, it says the definition of mole fraction is shown above. Calculate the mole fraction of hydrogen and methane in this gas mixture. Now, initially, you might be tempted to use the ideal gas law to calculate the number of moles, but unfortunately, we don't know the temperature of the gas, so we can't use the ideal gas law because there's not enough information to calculate the number of moles. So what we can do is remember that there is a direct relationship between pressure and number of moles. So if I have a relationship between pressure and number of moles, and that's a direct relationship, then the ratio of moles is going to be the same as the ratio of pressure. So here on the equation sheet, we have the equation for partial pressure. The partial pressure of a gas in a mixture is equal to the total pressure of the gas mixture times the mole fraction. Watch what happens if we simply divide both sides of this equation by the total pressure. So by doing that, we've just solved for the mole fraction in terms of a pressure ratio. Remember that pressure and moles are proportional to each other, assuming we have constant temperature and constant volume. So the ratio of the partial pressure of one gas divided by the total pressure of the gas mixture, that is equal to the mole fraction. That's exactly what we're trying to find in part B. So all we have to do to calculate the mole fraction of each gas is simply set up a pressure ratio. So the pressure of one gas divided by the total pressure will give us the numerical value for mole fraction. Let's go ahead and use the numbers that we have. So it's going to be for hydrogen, 2.14 atmospheres, the partial pressure of hydrogen, divided by the total pressure of the gas mixture, 2.71 atmospheres. And when we do that math, we get 0.79. Let's do a similar calculation for the methane, CH4. The partial pressure of the methane, 0.571 atmospheres, divided by the total pressure of the gas mixture, 2.71 atmospheres. Do that math and we get 0.21. So these values, 0.79 and 0.21, represent the mole fraction of hydrogen and the mole fraction of methane, respectively. So these are the correct answers to part B of question 12. Now, before we take a look at question 13, here's some information about collecting a gas by a method known as water displacement. In the laboratory, water displacement can be used to collect a sample of gas. This technique is appropriate to collect a gas that does not react with water or dissolve very much in water. A collection bottle is prepared that is initially filled with water and inverted in a container of water. Once the gas has been collected, again, it displaces the water, so the gas goes in, pushing some of the water out. The collection bottle is raised or lowered so that the water level inside the bottle is the same as the water level outside the bottle. And this is done to ensure that the gas pressure inside the bottle is equal to the atmospheric pressure or the barometric pressure outside the bottle. Now, since there's water inside that collection bottle, the total pressure inside the collection bottle is a mixture. It's equal to the sum of the partial pressure of whatever gas you collected plus the vapor pressure of water. So the total pressure is the sum of the pressure of the gas collected and the vapor pressure of the water. And you can look them up in a table. You can look up values for the vapor pressure of water at various temperatures in a reference table. So this equation says that the total pressure of the gas that was collected in this gas collection bottle is equal to the atmospheric pressure or the barometric pressure, and it's the sum of the pressure of the gas collected plus the vapor pressure of water at a particular temperature. Now, let's take a look at question 13. Question 13 says, a sample of butane gas was collected by the method of water displacement. The initial mass of a butane lighter is recorded as 22.24 grams. The temperature of the water bath is 22 degrees Celsius. The barometric pressure in the laboratory is 755 torr. After the butane gas is collected, the mass of the butane lighter is recorded as 22.02 grams. So there was a difference in mass. At the end of the experiment, the height of the collection tube is adjusted so that the water levels inside and outside the tube are the same. Part A. Based on the information in the table above, which is vapor pressure of water at different temperatures, what is the value for the vapor pressure of water under the conditions of the experiment? So in the table, we can see temperatures of 20, 21, 22, and 23 degrees Celsius with various values for the vapor pressure of water. And since we are told in the description of the experiment that the temperature of the water bath is equal to 22 degrees Celsius. So looking at the data in the table, we can see that when the temperature of water is 22 degrees Celsius, the vapor pressure of water has a value of 19.83 torr. So the vapor pressure of water at a temperature of 22 degrees Celsius is equal to 19.83 torr, and that's the answer to part A. Now let's take a look at part B of this question. Part B says calculate the partial pressure of the dry butane gas that is collected in this experiment. And you might be wondering, why do they say dry butane gas? Well, the reason why they say dry is without water. So during the method of water displacement, you will have a mixture of whatever gas you're trying to collect mixed in with a little bit of water vapor. So dry butane means just the butane without the water. So the total pressure inside the collection bottle in this experiment is equal to the sum of the partial pressure of the gas collected, that would be butane, and the vapor pressure of water. And values for the vapor pressure of water can be found in a reference table, which we've already determined in part A was 19.83 torr. So the barometric pressure in the laboratory during this experiment is 755 torr. And at the end of the experiment, the height of the collection tube is adjusted so that the water levels inside and outside the tube are the same. That means that the total pressure is equal to the atmosphere or the barometric pressure, which is 755 torr. And that number, 755 torr, is the pressure of the mixture of butane plus a little bit of water vapor. So since the total pressure is 755 torr, the pressure of just the water is 19.83 torr. That means that the difference between 755 and 19.83, that will represent the value for the partial pressure of butane without the water, so the dry butane gas. So 755 minus 19.83, that gives us a value of 735.17 torr. That number is the pressure of just the butane without the water. So that is the answer to part B, 735.17 torr. Now, let's take a look at part C of this question. In part C, it says the volume of butane gas collected in this experiment is recorded as 100.0 milliliters. Calculate the number of moles of butane gas collected in this experiment. Assume that the temperature of the butane gas is the same as the temperature of the water bath. Now, if you're wondering, are we going to use the ideal gas law in this calculation? The answer is we can use the ideal gas law as long as we know 3 of the 4 variables. So those 3 variables would be temperature, pressure, and volume. So we have the temperature of the water bath, and that is in degrees Celsius. So we're going to add 273 to the Celsius temperature. So 22 degrees Celsius plus 273, that's 295 Kelvin. And it says assume the temperature of the butane gas is the same as the temperature of the water bath. So now we have the temperature of the gas, we have the pressure of the gas, and we have the volume. So we're going to use the ideal gas law to calculate the number of moles. The ideal gas law is PV equals nRT, pressure in atmospheres, volume in liters, temperature in Kelvin, and the ideal gas law constant R is 0.08206. So here is our ideal gas law. Let's go ahead and calculate the number of moles by solving for N. So N represents the number of moles. So N equals P times V divided by R times T. Now the pressure is supposed to be in atmospheres, but right now the pressure of the butane from part B is 735.17 torr. Remember how to convert from torr into atmospheres. From the equation sheet, 1 atmosphere is equal to 760 torr. Let's take our pressure of butane, 735.17 torr, set up a conversion factor involving 1 atmosphere over 760 torr. Pick up your calculator and do 735.17 divided by 760, and then that would be the pressure of the butane gas in atmospheres. And that works out to be 0.96733, and I'm using all 5 significant figures based on that pressure in torr, which also has 5 significant figures. Now for the volume, they told us that the volume is 100.0 milliliters. Remember that when you go from milliliters to liters, you divide by 1,000. So 100 divided by 1,000 gives us a value of 0.1 liters. And I'm using all 4 of the significant figures in that calculation. The ideal gas constant is 0.08206. The units of the ideal gas constant are liters, atmospheres per mole per Kelvin. And the temperature of the gas we have already calculated is 295 Kelvin. So the answer to part C is the number of moles of butane gas. 0.96733 times 0.1 divided by 0.08206 divided by 295. This is what I got on my calculator before I rounded off my answer, 0.003996 moles of butane gas. And based on the least number of significant figures, that would be 3, I'm going to round this off to 0.00400. So that is my answer for the number of moles of butane gas, and I used the ideal gas law to do that calculation. All right, now let's take a look at part D of this question. In part D, it says calculate the mass of butane gas collected in this experiment. So the initial mass of the butane lighter was 22.24 grams. And after the gas is collected, the mass of that butane lighter is recorded as 22.02. So what's the difference in mass? That would represent how much butane gas was collected in this experiment. So 22.24 minus 22.02, that gives us a value of 0.22 grams of butane. That's the answer to part D. Remember that molar mass would be grams per mole, or grams divided by moles. So let's take the answer to part D, which is grams of butane, and then we can divide by the answer that we had calculated in part C, which was 0.00400 moles. Grams divided by moles will give us the units of grams per mole, or molar mass. So 0.22 grams of butane divided by 0.00400 moles of butane. When we do that math, we get a value of 55 grams per mole. So that is the answer to part E, the experimental value for the molar mass of butane. Now, in part F of this question, we're going to calculate the percent error for the molar mass value that was obtained in this experiment. So the difference between the experimental value and the accepted value would be the number that we got from the laboratory calculations, which is 55 grams per mole, and then butane, C4H10, using the information on the periodic table, has an accepted value for the molar mass of 58.12. So we can subtract the difference between 55 and 58.12 and just take the absolute value of that difference to avoid any negative sign in your answer. That's going to work out to be 3.12, which is the difference, divided by 58.12 and then times 100. And if you do that math, you should get a value for percent error of approximately 5.4% error. So that is the answer to part F of this question. Now, let's take a look at question 14. Question 14 says, a sample of a pure gaseous hydrocarbon is introduced into a previously evacuated rigid 1-liter vessel. The pressure of the gas is 0.2 atmospheres at a temperature of 127 degrees Celsius. Part A. Calculate the number of moles of the hydrocarbon in the vessel. So if we're trying to calculate the number of moles of this particular gaseous hydrocarbon sample, we can use the ideal gas law to do that, as long as we know the pressure, the volume, and the temperature of this gas sample. Again, the value of the ideal gas constant R would be 0.08206, and the units of volume should be in liters, pressure should be in atmospheres, temperature should be in Kelvin. So PV equals nRT. We're going to solve for the number of moles, which is N. N is equal to P times V divided by R times T. So the pressure is given to us as 0.200 atmospheres. That's the correct unit of atmosphere, so we can just plug that number directly into our setup for this calculation. The volume is 1 liter. Again, the units of volume should be in liters, so no need to change that value. R is 0.08206 liters, atmospheres per mole per Kelvin, but the temperature is right now listed as 127 degrees Celsius. And the conversion factor to go from Celsius to Kelvin is that we add 273 to the Celsius temperature. So 127 plus 273 gives us a value for temperature of 400 Kelvin. So now let's pick up our calculator and calculate the number of moles of the hydrocarbon in the vessel. 0.2 times 1 divided by 0.08206 divided by 400. And so we get a value of 0.006093. I'm going to round off my answer to 3 significant figures based on the measurements I was given. So I'll say 0.00609 moles. That's the number of moles of the hydrocarbon in the vessel. Now let's take a look at part B of this question. It says that oxygen gas is introduced into the same vessel containing the hydrocarbon. After the addition of the oxygen gas, the total pressure of the gas mixture in the vessel is equal to 1.40 atmospheres at a temperature of 127 degrees Celsius. Calculate the partial pressure of the oxygen in the vessel. So 1.40 atmospheres is not the pressure of the oxygen, it's the pressure of the gas mixture. And there's already a hydrocarbon which has a partial pressure of 0.200 atmospheres. Remember that the total pressure is simply the sum of the individual partial pressures of the gases in the mixture. So if the total pressure is 1.40 atmospheres, and that is the sum of the partial pressure of the hydrocarbon, which we have already determined is 0.2 atmospheres, then let's just subtract these two numbers to get the partial pressure of the oxygen gas. So 1.4 minus 0.2 gives us a value of 1.2 atmospheres. That is the partial pressure of the oxygen in the vessel. Now let's take a look at part C of this question. It says the mixture of the hydrocarbon and the oxygen gas is sparked so that a combustion reaction occurs. So they're initiating a chemical reaction between this hydrocarbon and oxygen. And it produces carbon dioxide gas and water vapor. Now, this chemical reaction proceeds to completion so that all of the hydrocarbon is consumed. There is some oxygen gas remaining in the reaction vessel after the reaction is complete. The temperature inside the reaction vessel is returned to 127 degrees Celsius, and the partial pressure of each gas in the reaction vessel at the end of the reaction are shown in the table below. So there's no more hydrocarbon that was completely consumed, but we have carbon dioxide gas, 0.6 atmospheres. We have water vapor, 0.8 atmospheres, and then there's some oxygen gas remaining left over after the reaction is complete, and that was 0.2 atmospheres. So in part C of this question, we need to calculate each of the following quantities, and you can see that each of these quantities is a mole ratio. The first quantity says moles of carbon dioxide gas produced over moles of hydrocarbon consumed. And then the other quantity is similar. It's a mole ratio. Moles of water vapor produced over moles of hydrocarbon consumed. But what we have is pressure data in this table. So how can we use the pressure data to determine the mole ratio? Now, you may recall from earlier in this video that one of the direct relationships in terms of gas variables was pressure and moles. That pressure is directly proportional to the number of moles. Assuming that the variables of volume and temperature are constant, the mole ratio is the same as the pressure ratio in a gas mixture. So since pressure and moles are directly proportional, and in this problem, we're not changing the temperature, it's still 127 degrees Celsius. We're not changing the volume, it's a rigid 1 liter reaction vessel. We can go ahead and set up a proportion comparing moles and pressure. So let's take a look at that first ratio. What they want is the moles of carbon dioxide gas produced over the moles of hydrocarbon consumed? Well, we have data for the pressure of CO2 at the end of the experiment, which is 0.6 atmospheres. And then at the very beginning of this question, they said that the pressure of the hydrocarbon at the very beginning, before the reaction occurred, was 0.2 atmospheres. So that ratio would be 0.6, the pressure of CO2, divided by 0.2. And even though those are pressure ratios, it's the same as the mole ratio. So 0.6 divided by 0.2 is equal to 3. So the mole ratio of CO2 to hydrocarbon is 3. Let's do a similar calculation for the water. Moles of water vapor produced divided by moles of hydrocarbon consumed is equal to the pressure ratio. So the pressure of water vapor at the end of the experiment is 0.8 atmospheres. The initial pressure of the hydrocarbon was 0.2 atmospheres. So that ratio of 0.8 divided by 0.2 is equal to 4. And that pressure ratio is the same as the mole ratio. Well, now that we have numbers of 3 and 4 for those respective mole ratios, let's take a look at the next part of this question. This is part D. It says determine the chemical formula of the hydrocarbon and write the balanced chemical equation for the combustion reaction that occurred in this experiment. Now, initially, you might think this is impossible because we don't know anything about the chemical formula of the hydrocarbon. I've just written CXHY as X and Y are unknown numbers for the subscripts of the chemical formula of the hydrocarbon. We know that a chemical reaction occurred with oxygen and the hydrocarbon producing carbon dioxide and water. Now, based on the answers to part C, the ratio of moles of carbon dioxide produced to moles of hydrocarbon consumed is a 3-to-1 ratio. Let's assume I have 1 mole of hydrocarbon. I would have 3 moles of CO2 for every 1 mole of hydrocarbon. And then for the water, we had already determined in part C that the ratio of moles of water produced over moles of hydrocarbon consumed is a 4-to-1 ratio. So there would be 4 moles of water for every 1 mole of hydrocarbon. Now, the instructions in part D said determine the chemical formula of the hydrocarbon and write the balanced chemical equation for the combustion reaction that occurred. Well, we're almost done with the answer for the chemical formula of the hydrocarbon. There are 3 moles of carbon on the right side of the equation for every 8 moles of H, individual hydrogen. So 3 moles of C for every 8 moles of H. That will give us the subscripts that we need to write the chemical formula of the hydrocarbon. So the hydrocarbon must be C3H8. And now all we have to do is balance this combustion equation. So there's 3 carbons on both sides of the equation. There's 8 hydrogens on both sides of the equation. But I can see a total of 3 times 2, which is 6, plus 4. That would be 10 oxygen atoms on the right side of the equation. And if there's 10 atoms of oxygen on the right side of the equation, I could just put a 5 in front of the O2 on the left. So now this is not only the chemical formula of the hydrocarbon, C3H8, but this is the answer for the balanced chemical equation for the combustion reaction that occurred in this experiment. And it all came from our understanding of mole ratios, which was related to the pressure ratio in that reaction vessel. All right, well, let's go ahead and take a look at part E of this question. Part E says calculate the mass of the hydrocarbon that was consumed in this experiment. Now, initially the hydrocarbon was unknown, but now we know that this hydrocarbon is C3H8. The number of moles of the hydrocarbon that were consumed in this experiment, going back to part A, was 0.00609 moles. We know that the identity of the hydrocarbon is C3H8. And on the periodic table, we can figure out the molar mass of C3H8 and now convert moles into grams. So the molar mass of C3H8 is 44.094 grams per mole. We can set up a conversion factor to go from moles to grams. 0.00609 moles of this hydrocarbon, that was from part A, times the molar mass of the hydrocarbon, which is C3H8. That gives us a value 0.268532, which I'm not rounding off yet. Let me go ahead and round off this answer to 3 significant figures, and that will give me a value of 0.269. That's the number of grams, or the mass, of the hydrocarbon, C3H8, that was consumed in this experiment. All right, well, part E of question 14, that is the last part of this question. It's also the last question in this packet. So, this is the end of the video. I hope that you found all of these answers and explanations helpful. Thanks for watching.